Recording in progress.
Yeah, comes on everyone. Let's start off. The last thing we are doing moment of inertia. Before going ahead, let's do one more problem. Okay, we did this thing also. Done. So let's go ahead. Next thing. Velocity and acceleration profile of a rolling body. Other scans on. So let's say we have a body which is rotating and translating. Now, if you remember in center of mass, we discussed this. You can split the motion into translation and rotation about the center of mass. Means you can assume that everything is going with speed v plus everything is rotating with omega. Means you can assume everything is going with v. This is going with v. This point is going with v. So every point on the rod is going with v. And here, since it is rotating, every point here is going with r omega. This point is going with r omega, r omega, r omega. So if you take any point somewhere in the middle like this, then this will be small r omega. So basically everyone is going in circles. Clear with us? So if someone asks you to find the velocity, you simply take the velocity from the translation and velocity from the rotation, and then you combine them. Yeah. So example, so let's say this is going with v and this is going with omega. And if I ask you to find the velocity of this point A, velocity of this point B, velocity of this point C, and this point D, and let's say some point in the middle, somewhere here E, at an angle theta and distance r. So now what you can do, you can simply split this velocity. So there are like two components. So due to translation, everyone will be going with v horizontally. And due to rotation, everyone will be going with r omega, r omega, r omega, r omega, and this distance will be r omega. So if you want to find the velocity of A, you add it from, this is pure translation. And this is pure rotation about center of mass. Remember, you can do this only about center of mass. That is the whole definition of center of mass. Center of mass is a point about which you can spread the motion. Now, in case of a rolling body, center is fine, but generally, when you are just flying in the air, you take the center of mass. So velocity of A will be V I cap, that is due to the translation, plus R omega due to rotation. So VA will be V plus R omega I cap. So you simply add the velocity from translation, add the velocity from rotation, and then add them up. So velocity at B due to rotation, translation is V I cap, and rotation will be minus R omega J cap. Velocity at C will be V minus R omega I cap. And velocity at D will be V I cap and R omega J cap. And velocity at E, so there we have to resolve this. If you take this angle as theta, that is theta. So this angle will be 90 minus theta. So velocity at E will be V I cap plus R omega cos 90 minus theta I cap minus R omega sin 90 minus theta J cap. So you resolve them into components. So this will be V plus R omega sin theta I cap minus R omega cos theta J cap. Is that clear, everyone? So you simply split the motion into translation and rotation, get the translation velocity, get the rotation velocity, and add them up. Is the idea clear? Srihari, clear with that? Rudransh? Rudransh can't see you, adjust your camera. Shaurya? Rudransh, are you there? Okay. Let's see a question. That's it. So simple thing. So you split the motion to translation and rotation and add them up. So let's say we got a disk. The disk is going with velocity v. It's rotating backward with omega 3v by r. Let's say we have a point A here, which is making an angle of 120 degrees. And this distance is r by 2. This is the disk. So find velocity at A and find the position whose velocity is 0. Or let me ask you this way. Find the position. Find a point on the disk whose velocity is along y-axis. So the velocity should point in the upward direction. I can even ask you this thing. Find the point where the velocity is 0, something of that sort. But anyway, there will be some point on the disk which will be pointing upward, the velocity at that instant. Same story. Split the motion into translation, rotation, finish it off. You didn't get this thing? I thought you guys will get the velocity of A. See. So you have to add the translation and the rotation. So point A, the translation will be V this way. Rotation will be this way. It's going in this circle here. That is R by 2 omega. So if that is 120, this angle will be 60. If that is 60, that will be 30, and this angle will be 60. So there. So at point A, we can resolve the velocities. This will be V. This will be R omega by 2 cos 60. And this will be R omega by 2 sine 60. And we can clearly see R omega is nothing but 3V. Therefore, velocity of A will be V minus R omega is 3V by 2, sine 60 is root 3 by 2 I cap, minus R omega is 3V by 4 J cap. Check. That's your velocity at point A. Is that making sense? See where it went wrong? Here, omega is 3V by R. It's given, getting it? So don't assume any random omega when it is given. 3V by 2. So how did you get J cap, right? You'll get minus J cap. Any doubts on this? Did I do any calculation mistake here? Clear? What's the second part of the equation? Find the point where the velocity is in the vertical direction. How do we do that? Same thing, since we don't know where is the point, let the point be at a distance x and let the angle be theta. So x and theta both are variables. So this point will have a transition velocity v this way. And remember, omega is rotating this way. So r omega will be, x omega will be this way. So this point has velocity v this way and x omega this way. This angle was theta. If this is theta, this is theta, this is a 90 minus theta. Remember, the velocity will be perpendicular to the r bar. So now if you resolve the velocities, we have v this way, and we have x omega cos 90 minus theta, and x omega cos theta. And it is given in the question, velocity should be in the vertical direction. Since velocity is along y direction, means vx is 0. Since velocity is along y direction, vx must be 0. Therefore, v must be v minus x omega sine theta is equal to 0. And what is omega? Omega is 3v by r. So this will be v is equal to x omega 3v by r sine theta. So we got x into sine theta must be r by 3. There actually we're not getting a single answer. We are getting multiple values there. So as long as this x and theta is satisfied, so there are not a single answer. There are infinite answers. There are infinite points on this disk where the velocity will be in the vertical direction, which depends on x and theta. So if you fix at least any one of them, if you tell me, right, find the distance and the angle of 45, then I can find x. Are you clear with this? And you can actually play a lot with this thing. So if you look at this sine theta, which is r by 3x, which is less than equal to 1, that point x must be greater than equal to r by 3. So they can ask a question like this also. Wherever is that point, it should definitely exist outside the circle, which is more than r by 3. You're getting how they can frame a question? Is that making sense? So that point, whichever is that, will exist definitely outside r by 3 radius. So there is no point within the disk from 0 to r by 3 which can have a velocity in the vertical direction. So there are infinite answers. There's no single answer here. Is this clear? There, you can play like that. Any doubts on this? So x into sine theta is constant. That is the locus of all the points where the velocity is in the vertical direction. So for different thetas, you get different x. Clear with this? Next thing. So that is how you can find velocities on the disk. Acceleration profile. Now, unlike velocity, acceleration is interesting. Huh? It has something more. So if you have a disk which has acceleration of center of mass, so this is your translation. Remember, center of mass will always take care of translation. And let's say the body is rotating with alpha. This is your angular acceleration. Now, and let's say at that instant, you also have omega. Now look at this thing. If someone asks you to find acceleration at any point on the disk or the ring, so if you look at this point here, we have a center of mass. This is due to translation. And we have a tangential, which is r alpha. And since you're going in a circle, there will be also a centripetal acceleration, omega square r. So every point on the disk or the ring will have three accelerations. If you see, in case of a velocity, we had translation velocity and rotational velocity, right? Same way, if you take at this point here, acceleration of center of mass, right? And this will be your A tangential, which is R alpha, omega square R centripetal acceleration. So there'll be three accelerations at every point. Omega square R, omega square R, A center of mass, R alpha, A center of mass, R alpha. There. So if someone asks you find the acceleration of any particular point, you have to take the resultant of all these three accelerations. If you remember, in non-uniform circular motion, every point used to have two accelerations, tangential and centripetal. Now you're adding translation to it. Is this clear, everyone? There. Now you know how the velocity profile of a velocity profile and acceleration profile works. Now, what is a no slipping condition? This is the most important thing. So first, let me ask you this: what is no slipping exactly? This is not the first time you already heard this word in friction. Most people think no slipping matlab not moving. Not necessary. No slipping means simply the surfaces in contact have zero relative velocity or they're going together. They should have same velocity and same acceleration. Then we can say the body is not slipping. So example, let's say we got a cylinder which is on top of a plank. Let's say plank is going with Vp. This is going with V center of mass, and let's say this is going with omega. And let's say plank is accelerating with AP. Let's say the cylinder is accelerating with center of mass, and this is going with alpha. Now, if you took this cylinder and the plank separately, so we are interested in the points of contact. Again, understand, we don't care about the full body velocity. We are only interested in the points which are touching each other. So if you look at the velocity, it has translation velocity v center of mass forward. It has v tangential r omega backward. And this point will have v plank forward. Since it is not slipping, velocity at A must be equal to velocity at B. That is v center of mass minus v tangential must be equal to velocity of the plank. This is your no slipping condition. Again, don't remember this. Remember it like this. No slipping condition is the points in contact should have same velocity. So you must have studied in books or something. Now, what is no slipping condition? V is equal to r omega. That's a blunder. Never say V is equal to r omega is no slipping condition. That's a very special case. Similarly, if you look at the acceleration also, acceleration of A must be equal to acceleration of B. This will be A center of mass minus A tangential is equal to acceleration of plank. We get A center of mass minus R alpha is equal to AP. If the plank was at rest, that means you keep this on the ground. Then VP will be 0, AP will be 0. Then you get this case, V center of mass is equal to R omega, A center of mass is equal to R alpha. Be careful, V center of mass is didn't become R omega. V center of mass became equal to V tangential and V tangential is R omega. Are you clear with this? So if someone asks you what is no slipping condition, you should say at the points of contact, the relative velocity and relative acceleration are 0. That's it. Don't say V is equal to R omega and all that thing. Clear with this? Any doubts on this statement? Clear? That's it. If you got this, this is the third thing that I was saying, the no slipping condition. Let me show you a question. Let's do an easy one, then I'll show you something a little tougher. Let's say we have a plank, we have a cylinder, and we have a plank. Let's say this is plank 1, VP2. Let's say it is going with some 20 meters per second. Let's say this is plank 1, which is going with 10 meters per second. And this thing has a radius of 2 meters. Find the velocity and omega of the cylinder if there is no slipping at any surface. If there is no slipping between cylinder and the planks. So we have plank 2 and plank 1. And between them, we have a solid cylinder stuck between them. Meaning this is how the picture will look after some time. The plank will be here, the cylinder will be here, this plank will be here. So they're kind of sliding. So don't worry, it will not fall down. Ignore all that. If there's no slipping between cylinder and the planks, find the velocity v and omega of the cylinder. This is the third thing. You know already how to calculate torque. You know how to already calculate moment of inertia. Now, if you know how to apply no slipping condition, I think all our ingredients are ready. Try. Take a minute. Okay, a few people got some answers. Looks right. Others, try. I'll give you a minute. I want everyone to try. It's okay to get a wrong answer. It's an important one. No slipping condition. How do we start? So, general idea, in case you're wondering, okay, how do I exactly start this? What did I ask you? Velocity of the cylinder and omega of the cylinder. You don't know, na? Assume. Let this be VCOM and let this be omega. Don't worry about this, science will take care of it. So, if you take the cylinder, now go back to the velocity profile. Since you're rotating, the topmost point will have V center of mass forward, R omega also forward. This will have V center of mass forward. I'll just write plus directly. And this thing is R omega backward. Perfect. So we have a plank on top of it. We have a plank at the bottom. So again, you're interested in the points of contact. So this point and this point are touching each other. And this is going with what? 20 meters per second. This point and this point are touching each other. And there's no slipping. So this point is going with 10 meters per second. So the first equation, V center of mass plus R omega must be equal to 20 since you didn't slip. V center of mass minus R omega must be 10 since you didn't slip. Add them, you will end up with V center of mass is equal to 30 by 2, 15. Put 15 back there and we get R omega is equal to 5 and omega is 5 by 2. In case if you have taken omega or V wrong, the signs will take care of themselves. You need not worry. You just assume any direction. Is that clear, everyone? Easy? Let's do something a little tougher. But this is the idea behind this. Any doubts? Clear, na, Vanchika? Sudiksha? Shaunak? Rudransh? Let's see one more. Clear, no, Abhya? Great. Let's say we have two cylinders. Both are placed on the ground. On top of them, you kept a plank. On top of them, you kept two more cylinders. On top of them, you kept a plank. Right. So let's say this is rotating with omega. This is rotating with omega. This is rotating anti-clockwise 2 omega. This is rotating anti-clockwise 2 omega. This is Planck 2 ka velocity. We don't know. This is VP1. We don't know. This cylinders also must be translating. So V1, we don't know. This is V2. That also we don't know. So we don't know any translation velocity here, right? And there's no slipping at any surface. The cylinders are not slipping on the ground. The cylinder and the plank 1 is not slipping. Cylinders and the plank 2 are not slipping. Nothing is slipping. There is no slipping at any surface. Find all the velocities. There. This is a good one. R is the radius of the cylinder. Both the cylinders. Identical cylinders, they're just rotating in different directions. The bottom two cylinders are rotating with omega, upper two cylinders are rotating 2 omega anticlockwise. Find the velocity of cylinders and planks. There, let's get this. Hope the picture is clear, everyone. Guys, I'm just going to remove you from the classroom if you just keep switching off your cameras. I don't know why you're doing this. I can tell you once or twice to put your cam on, but if you're going to do this repeatedly, I'm just going to block you. So and if there's a reason, something, you should message me. You just can't black out. That looks right, Samyak. Let's see. And please don't behave like this is your first class and as if you don't know anything about this. So You're getting a others. Try. आर्या एक बार चेक करो VP2. I think you got reverse.
So it's just the magnitude.
Get me the velocities. एग्जाम में यही बोलो -1 आ जाएगा and then you cry. That was a lot. Let's see. Let's see. So let's start from the bottom. Let's take the lower cylinder. We don't know the velocity, so this guy is going with V1 and omega. So the topmost point will have a velocity V1 plus R omega. The bottom point will have velocity V1 minus R omega. And this is the ground. So the bottommost point is touching the ground. So this point and this point, so V1 minus R omega must be equal to V ground. But I know ground is not moving, so that is 0. Therefore, V1 is equal to R omega. There we got 1. On top of this, we have Planck 1. And we know this point is going with VP1. Since this point and this point are not slipping, V1 plus R omega must be VP1. But just now I found V1 is R omega. So VP1 must be 2R omega. There I got the velocity of Planck 1. On top of this, we have this cylinder which is going with V2 and rotating this way with omega, 2 omega. That means this point will have a velocity V2 plus 2R omega, and this point will have a velocity V2 minus 2R omega. But we know this point and this point will have same velocity because they're not slipping. So that is the story every time. Whoever is touching, they should have same velocity, VP1. But I know VP1 is 2R omega. Therefore, V2 is 0. That means the upper cylinders are not translating, they're just rotating at the same place. And now if you connect that to the Planck on the top, this point and this point should have same velocity. That is VP2. So VP2 must be equal to V2 minus 2R omega. But V2 is 0. Therefore, VP2 is minus 2R omega. So the topmost Planck is actually going backward. Are you clear how we did this? One step at a time. You just keep connecting the lower surface to the upper surface and so on. Please have a look at this. This is important. Anything that you're not convinced, not clear, any doubt, please ask. How did I get that velocity? Why did I equate those two? How did I get V plus, V minus? Anything you're not clear, please ask. If you got this, you understood no slipping conditions. Meaning there is still more variety, but we will see them in the problems. But this is the basic thing. If two surfaces are touching and you say it is not slipping, at the point of contact, they should have same velocity. The bodies need not have same velocity. All clear with this? Advai, Devanshi, Vedika, Sudiksha, Srihari, Pratyasha. Great. There. Now we have all the ingredients. You know how to calculate torque. You know how to calculate moment of inertia. You know how to use no slipping condition. So when a problem is given, how do you solve? Steps to solve. Same thing. Choose your system, draw your FBD. This will be standard, like doesn't matter. And you already know how to draw FBD. I taught you this in equilibrium. Again, you need to understand every time you won't be learning completely new. 60-70% will be old stuff only. Second thing, assign. So since things are moving, so assign linear accelerations. So if there are three bodies, right, and all are moving, then assign accelerations A1, A2, A3. And if they're also rotating, assign alpha 1, alpha 2, alpha 3. So assign linear and angular accelerations and find the relation between them using constraints, which is laws of motion. So if there are three bodies going with A1, A2, A3, there will be some relation between them. So find the relation between them using constraints, string constraints and rigid body constraints. And no slipping condition. Step 3, apply F is equal to ma along two perpendicular directions. So resolve the forces along x and y axis and apply F is equal to ma. This is again completely laws of motion. Fourth, apply torque is equal to I alpha. Now be careful here. When you say torque, if you take torque about an axis, then I also must be about the same axis. You can't take torque about A and I about B. It doesn't work like that. But there's few things here. Preferably, whenever you're trying to take torque, right? Preferably take about a fixed point, like a hinge or something, about a point in inertial frame, because you don't want to apply pseudo force. But if you cannot find any point which is in inertial frame, then center of mass. Center of mass is always the safest point, and you will see why. Suppose if you're standing in a non-inertial frame, then your torque equation becomes torque due to external. You have to include the torque due to pseudo force also, is equal to I alpha. Now, why center of mass is so special? If you take torque about center of mass, the torque about the pseudo force will be zero. Why? Because pseudo force passes through the center of mass. Tell me one thing. When you have to apply pseudo force on a body, where do you apply? You apply it on center of mass. And if a force passes through the center of mass, then torque about center of mass is zero. Arya.
So the equation which you wrote, like torque external plus torque pseudo is equals to I alpha, it's not always valid, right?
Let's not go there now.
Okay.
You know, right? You know when it is not valid. So you need to understand, right? Just because you know it doesn't mean others know. Na? I have to teach it in a way where we slowly consume it. You're talking about variable movement of inertia.
Not only that, sir, like the torque about axis and torque about point have to be equal for that.
We're not talking about points of rotation. We are talking about axis of rotations only. Is that what you're
Okay,
saying?
sir. Like not always it will be that the torque about a point is torque about axis.
No, na, because point of rotation is three axis. We didn't define that, right? Already. इसीलिए तो axis लेगा मैंने. Clear with this? Because I didn't teach you how to calculate moment of inertia about a point. That will become a tensor quantity. We don't want to deal with that. Anyways, so clear with the steps. Please have a look at this page once. So no matter what problem I'm going to give you now, this is the process. You draw the FBD, right? You assign linear and angular accelerations. You find the relation between them. Apply F is equal to ma. Then apply torque equation. Preferably about a point which is fixed or which going with constant velocity, inertial frame basically, or center of mass. And then you solve the equations. Clear with the steps? Let's start off with something simple and then we'll slowly build it up. Let's say we have a rod here. Mass m, length L, gravity is there. So you took a scissor and you cut at this point. Find alpha of the rod, acceleration of point A, and hinge reaction just after the string is cut. Because the moment you cut the string, the rod will try to swing like this. So things will start moving. And hinge reaction just after cutting. There. This is an easy one. Let's see how you handle this. Think for a minute, then I'll show you one model. Get me the hinge reaction also. Let's see. Yeah, right, Samyak. Right, Utsav. See, step one. Choose your system. Rod is my system. Draw the FBD. NY. Remember, whenever you see a hinge, draw two hinge reactions. The weight mg. Since you cut the string, there is no tension, gone. So there are only three forces. Step two, SN accelerations. So let the rod go with alpha. Remember, this is your center of mass. So center of mass is also going in a circle. But it is going in a circle of radius r by 2. So acceleration of center of mass will be L by 2 alpha. That is the relation between angular acceleration and center of mass. Clear? Because the center of mass will go in a circle of radius L by 2. Step 3, apply the force equations. In the vertical direction, the force equation will be mg minus ny, or I'll just keep it normal, ny minus mg mass into minus acceleration of center of mass since it is going down. Horizontal direction nx, there is no other force, nx is 0. Fourth step, apply torque equation about any fixed point or center of mass. Here, clearly we can see the hinge is a fixed point. If you can get a fixed point, that's always best. Take torque about A. Torque about A, torque due to nx is 0, torque due to ny is 0. The only percent torque left is mg. That will be mg into L by 2. That must be equal to, but we know torque about A is nothing but equal to I about A into alpha. What is the moment of inertia about the end of the rod? You guys remember the result? Mg L by 2 is equal to ml square by 3 alpha. This is what I was saying. If you don't know how to calculate torque or if you don't know the moment of inertia of values, you will be stuck. This was the reason we have done those thoroughly, like each and everything in detail. And this is the reason why people find rotation tough. Not because it is tough, but there are 3 to 4 parts and you have to be thorough with each one of them. You directly jump into the problem, whole thing will look like a mess. This will be 3g by 12. Point A is in this corner. Remember, A is also going on its own circle. The acceleration of A will be L alpha, which is 3g by 2. And normal reaction Ny will be mg minus m, A center of mass, but A center of mass is ml alpha by 2. But L alpha is this, so mg by 4. That's your hinge reaction. So the moment you cut the string, the hinge reaction suddenly goes from mg to mg by 4. Clear with this? Right, Arya. Right, Samya. Some of you got it. Are the steps clear, everyone? FBD, accelerations, force equations, torque, and solve. Arya.
So is there like any reason why the acceleration of A is more than G?
Because it is far.
Sir, I mean,
Why can't it be more than g? What is the problem?
in most of the questions, we saw that
But
when
here
the
it is
force is
connected,
applied,
na. That means this rod here is not pushing, it is pushing it down. That's why it is going faster than g.
okay. Like, sir,
Most
but
of the
why does
questions
the
we
rod pull?
saw, because rod can pull and push. What is the problem? Strings can't push, na. That's why we never got more than g.
Okay.
Right? It is basically most with the steel, See, if imagine if this had been blocks like this, you will see next question, you'll understand. Dvai, bolo na.
Sir, in that second step, how did you equate that ml square by 3 alpha? Where did you get that exactly?
You're asking how did you get I is ml square by 3?
Yeah.
Yeah, great question. Yeah, great question. You didn't bother to revise the notes, right? Did you bother to revise the notes? No, you didn't bother to revise the notes. That is ml square by 3. Right?
Yeah,
Now, if you
yeah,
had
I
bothered
did.
to revise the notes, you would have seen this not at one place, multiple places. This was the question there, ml square by 3.
Yeah, yes, sir.
And yeah.
Yes, sir.
So make sure to bother, be little careful, read the notes. Next one, same thing. I'm just going to change something. We'll put a hinge here, we'll put a string here, but this time we'll have a block here, mass m, error distance x. This is the string, huh? And this is cut. Same question, find alpha of the rod just after cutting. Or even better, plot alpha versus x graph. Or let me ask like this, find alpha is function of x just after cutting. So x is constant for a given situation, meaning x can be any value from 0 to 12. So I didn't tell you where I'm keeping the block. Same question as previous one, except this time I kept a block attached instead of this thing. Let's get this. Step 1, choose a system, draw the FBD. You understood now, yeah. So there are certain points which are going faster and certain points which are going slower. Strings can't push, but if that had been a rod, it wouldn't have mattered. Hmm. Let's see the FPD. You have to be careful here. The common mistake is this. Hinge reaction, NY. And next answer is not good. Mg. Till here it is great. Now be careful here. This is tension. Don't write Mg. The moment you write that is Mg, you're assuming the block is at rest. Okay? So when you write the block FBD separately, this will be tension and this will be Mg. These are the forces on the body. This is the FBD. Then let this be alpha, right? If this is going with alpha, then this point, right, will be going with X alpha. So this point will go with, how do we draw this X alpha? This is your center of mass. So your center of mass will go with A center of mass is L by 2 alpha. If that is going with X alpha, again, we're assuming string is still tight. So the acceleration of the block must be equal to X alpha. We will take care of that condition later on. But have a look at this. The red ones are the accelerations and the blue ones are the forces. नहीं रे आर्या, कुछ तो missing है तेरा. Denominator is messed up. There, I got the forces, I defined the accelerations, and I found the relation between them. Step 2, apply the force equations. So for the rod, Nx is 0, that is gone. Vertical direction mg minus ny is equal to mass into acceleration of center of mass. Great. And for the block here, it will be mg. Wait, I forgot there's a tension also. mg minus mg plus t minus ny is equal to m into a center of mass. And for the block, this is mg minus t is equal to m into acceleration of the block. These are the force equations. Next thing, let's write torque about the hinge. If I torque about the hinge, nx ka torque is 0, ny ka torque is 0, this will be t into x plus mg into L by 2. This is the torque. But I know torque is nothing but I about hinge into alpha. But what is tension? Tension will be mg minus ma block, but ma block is mx alpha. Take this thing and substitute here. And that will be mg minus mx alpha into x plus mg L by 2. What is I about the hinge? ml square by 3. We have taken the rod completely separately. So the block is not attached to the rod. If you ask the rod, what is the block? It will say, I don't know who is the block. All I can see there is a tension. This thing will be mg x plus mg L by 2 minus mx square alpha. So alpha will be, m will cancel everywhere, g x plus L by 2 by ml square by 3. But luckily, if you actually observe, the whole answer will come as if the block is attached to the rod at that point. But this is your alpha. The m is cancelled. This is not a linear function or something. This is a little weird. Question is not over. There's still a catch. But have a look at till here. Clear? Now what is the catch? There is a possibility. Look at the tension there which we got. Tension which is mg minus mx alpha. This should be always greater than equal to 0. That means x alpha must be always less than equal to g. And what is alpha ka value? Alpha ka value just now we got g into x plus L by 2, L square by 3 plus x square must be less than equal to g. G will cancel, we get x square plus xl by 2 must be equal to L square by 3 plus x square. We get x must be less than equal to 2L by 3. So there is a condition. So what happens is, if x is greater than 2L by 3, just look at the rod. If you remember the first question which we derived, when this point is going with alpha, which is 3g by 2L, there is a particular point on the rod, right, which is at a distance of 2L by 3. This guy is going with an acceleration g. Means after this point, all the other points are going faster than g, isn't it? All the points in this region, they go faster than g. So if a string is connected there, what will happen? See, if you leave a block, what is the maximum action the block can have? G, right? You can't have more than g. But if you're connecting a string at that point where it is going faster than g, what will happen? String becomes loose. If a string is connected in this region, tension becomes 0 because strings cannot push. So if you had connected the block greater than 2L by 3, the answer would have been the same as the previous question. Right, Arya. So therefore, what is your answer then? So alpha will be that weird result which you got, g into x plus L by 2 by x square plus L square by 3. This is valid for x less than equal to 2L by 3. And 3g by 2L, your regular answer, means as if the block doesn't exist for x greater than L and 2L by 3. There. They might not ask you to solve all this. They might ask you a simple question like, at what point should the block be connected so that the acceleration is independent of x? And if at all they try to ask you, maybe a graph, if you try to plot a graph between alpha and x, so if you connect the string at 0, it will not affect the problem, 3g by 2L. So the graph exactly, we're not sure, but one thing is clear, it will decrease, and then again somewhere it will increase, and then it becomes constant. This position will be 2L by 3. That much we can guess. The graph would look something of this sort. As you put the block away and away and away, it will decrease and then increase, and then it just becomes constant. When you consider t is equal to mg, what you're doing, you did two mistakes. When you consider t is equal to mg, did you take I is equal to ml square by 3 plus ml square? Did you consider the moment of inertia of the block also?
Of the moment of inertia block will take as mx square, right?
So that now say again your question only. If your system is the rod, why are you taking moment of inertia of the block?
Okay.
Got it? You did two mistakes. One, you took t is mg. Second, you took moment of inertia as you included the block. So what you did was you took the block and you attached to the rod here. So it worked out. So basically, as long as the string is tight, what you did was right. Clear with that? Other steps clear, everyone? This is a pretty good one. Matlab, you need to know where you're connecting the string also. Every point on the rod has different acceleration. Think about this. Ask me if there's any confusion on this. So the answer will change where you connect the block. Once you cross 12 by 3, it won't matter where you connect the block after 12 by 3. Because the moment you cut, string will become loose. Clear with this? Any doubts on this? There. The first question is a proper mains question. Second question will be a good advanced question. Go. Take a break. Come back by 9:40. We'll continue from here. Any doubts here? Anything that you're not clear, please ask. Chalo, come back in 5 minutes. Go away from the screen. The point of giving 5 minute break is that don't keep staring at the screen. Sure, let's start off. There, we have two similarly looking, identical looking situations, but in case one, the ground is rough, there is no slipping. That means this rod is simply going to fall like this. Meaning it behaves as if this is the hinge. But in the second case, the floor is smooth, meaning as the rod is falling, the rod also will start sliding like this. In both the cases, find alpha of the rod just after cutting. The first one is a mains question. It actually came in the exam. Second will be an advanced question. Other scams on. There, I'm trying to show you the same problem with little variations, like how it can become an advanced problem by changing few things. This is what I keep saying. Advanced problems are not some, out of the world problems, they do not ask you something completely new. You take a mains problem, you do some modifications or add 2 to 3 mains problems, it becomes an advanced one. So unless you're pretty confident with your mains level things, advanced, there's no point in thinking. Let's get the first one. The first one actually came in the exam. First case, so the rod is there at an angle theta. It is supported by a string. When you cut the string, rod starts falling. Find alpha of the rod just after cutting. In the first case, it's not slipping. Second case, it is smooth, so it will slip. Anyone not clear the picture, please ask. And others do keep your cams on. First one is right, Samir. Right, Upsa. Got the first one. Arya, Ovia, cams on. Let's see the first one. The first one you should have got. 3y to right. Right, Devanshi. Who else got it? One also got it. Shriyansh. So you got it. Yeah, Rudransh. Let's see the first one. Second is a really good one. Right? Step one, draw your FPD. The story is always the same. Huh? What are the forces? Normal reaction, friction, mg. I didn't ask you, but I can also ask you to find n and f at this instant. That will be a really good question. So at this instant, this is rotating with alpha. Remember, this is your center of mass. That also is going in a circle. So A center of mass is L by 2 alpha, right? So if this is A center of mass, this is theta, this is theta, this is 90 minus theta, then the horizontal component AX will be A center of mass cos 90 minus theta, which is sine theta. This will be AY is A center of mass cos theta. You don't need this to find alpha. So let's talk about this bottommost point. So torque about A, torque due to N is 0, torque due to F is 0, only mg ka torque will be there, mg L by 2 cos theta. And we know torque about the end will be Ia alpha, which is ml square by 3 alpha. There, you get it in one step if you just want alpha. And this was the main question. But if they ask you for N and F, then the horizontal force is only the friction, which is m into Ax, which is m into A center of mass, which is L alpha by 2 sine theta. There you can find friction from there. Mg minus normal reaction is equal to MAY. From here you can find normal reaction also. You know the alpha ka value, substitute here. Then you can find F and N from here. Clear with this? Then they can even ask you this question also. So then we can say friction F is less than equal to mu N. Then we even get mu ka value. So you can play around like that. So find the minimum mu required so that the rod does not slip initially. Clear with this? So even the first question you can ask them really good stuff. Now, any doubts on this? What about the second part? What if the floor is smooth? How do you handle that? Second thing, I'll give you some ideas. See, step one, choose your system. The rod is my system, draw the FBD. The problem with the second one, it looks too simple actually. That's the problem. There is no friction that actually creates a problem. So since the floor is smooth, there's a normal reaction, there is mg, that's it. There's no friction. There are no horizontal forces on the system. Therefore, we can actually make a statement like this. Since horizontal forces are zero, that means center of mass cannot go left and right. Therefore, a center of mass has to come down. Center of mass cannot go in any other direction. So accretion profile, the center of mass is coming down, and this is rotating with alpha. We still don't know the relation between A and alpha though. So now when I write the force equations, mg minus n is equal to macom. ठीक है. And be careful, I can't take torque about the corner. Since A is accelerating, A is actually going back. It is non-inertial frame, so don't take torque about that point. Previous one, it was not moving, it was not slipping, so it was fixed. It is non-inertial frame. So torque about A is not good. Not useful, it becomes complex. So the only guy you left is torque about center of mass will always work. So if I take torque about center of mass, you know the story, extend the force vector and drop the perpendicular. That is L by 2 cos theta. So torque about center of mass will be N into L by 2 cos theta. Torque about center of mass will be I center of mass into alpha. And do you know the center of mass? I about the center of mass? ml square by 12. The results are important. Perfect. We got equation 2. How many variables are there? We don't know n, we don't know alpha, we don't know A center of mass. We have 3 variables. And we have 2 equations, one force equation, one torque equation. Where will I get the third equation from? That's the whole catch in the question. Look at these steps. Ask me if you're confused here. And this is a pretty interesting thing. Matlab, if you look at the path of this particle, right, it actually goes like this. This was the rod. This was the center of mass. The rod will fall in such a way, the center of mass always has to fall down. It cannot go in any other direction. So next moment, the rod will look like this. The rod will come here. But the center of mass will still be here only. And then eventually the rod will become flat. And the center of mass will be here only. Are you getting it? The rod will fall in such a way, the center of mass is always falling straight. That itself is a mains question. What is the trajectory of a center of mass? Straight line. Where do I get the third equation from? So what is that, Srihari? What is the point of giving commentary? Find it, right? So what is that? You said something. So get it? Listen, this thing. Look at the point which is connecting the floor. First, let's find the acceleration profile. Look at this point. This is going down with A center of mass. And this is also rotating with alpha. So this point here, from acceleration profile, because of translation, you will be going down. And because of rotation about center of mass, you will be going in a circle in this direction with L by 2 alpha. But tell me one thing, can this point go up and down? Can that point go up and down? It cannot go, right? It is touching the ground always. It is sliding on the floor. Is that making sense? So if you just look at point A acceleration, it has a center of mass acting downward. If this angle is theta, this angle is 90 minus theta. Then this component will be L alpha by 2 cos 90 minus theta. And this component will be L alpha by 2 cos theta. So like Srihari said, rigid body constraint. Acceleration of point A along the normal, along the vertical must be 0 because it is always touching the floor. If it is not 0, means either it will go into the ground or it will give contact. This is where you get the third equation from. This is a rigid body constraint. This thing doesn't come from no slipping condition because here it is slipping. So we have A center of mass is equal to L alpha by 2 cos theta. Be careful. This is what I was saying. Blindly don't say A is equal to R alpha, no slipping condition. People do that. Check your 3 equations. Are you clear with the concept there? So first of all, the center mass is always falling straight. You need to figure that out. So force equation, you can't take torque about point A because A is sliding. It will have an acceleration. So it will be non-inertial frame. Take about center of mass. Third, the point A, it's not going up and down. So the acceleration must be 0. So if I take all the equations, now it is little work. Mg minus n is equal to ma COM. ml square alpha by 2 ml alpha by 6 is equal to n cos theta. A is equal to L alpha by 2 cos theta. There we have three equations, three unknowns. What do you want to find? You want to find alpha. So I don't want n. Okay. So n is equal to ml alpha by 6 cos theta. And take this n, substitute here. Take this a, substitute here. Dump everything in this. mg minus ml alpha by 6 cos theta. That is ml alpha by 2 cos theta. This will be g L alpha 1 by 6 cos theta by 2. That will be 6g cos theta by L. Hmm. If you multiply 3 there, 1 plus 3 cos square theta. Check. That's your alpha. You want asynchronous, we can find that also. Clear the steps. That's what makes the second problem an advanced one. Clear, Aditi? Go, wash your face and come. No? Fine. Any doubts on the steps? Why centromas will go up and down only? Right? Why can't you take torque about A? What is the rigid body constraint about the point A? Clear, Shman? Samyak? Phobia? Clear this? Trishi? Arya? Shaurya? Great. Next one. We have a disk here of mass m and radius r. And you started spinning this disk with an angular velocity omega naught. And then what you did, you placed it on a rough floor friction mu. Do you ever do this? You take a disk or a book or something, spin it, and just put it on a floor. So because of the friction, it will start slowing down, and finally stops. Find the time when the disk stops rotating. A rotating disk is placed on a rough surface as shown. Are you getting how? It's like your dosa. Getting it? I'm not keeping it like this. Huh? This is different. I'm keeping it like this, like a dosa, flat. So if that helps you to visualize, I'll write like that, like a dosa. Find the time when it stops rotating. Let's get this. This is a good one. Anyone not clear with the picture, please ask me. Try. It's a good one. I'll give you 2-3 minutes. Let's see how will you even approach. Meaning you have to integrate. That much I can tell you. Let's see. So first of all, forget about the question. Even just think about this. How is the friction acting on the disk in the first place? Right. So that is how you start thinking. Forget about the question. Don't be so obsessed about the answer when you're doing it for the first time. Try to think about all the possibilities. How is the friction acting? Is the friction same everywhere? If it is same, then how do we do that and everything? So let's see if you look at this from the top view or the bottom view. The friction. So if you say the disk is rotating with omega, again, remember friction is always opposite to the relative velocity between the points of contact. So the disk and the floor, when they're touching each other, right? Aditi, you got something 3r omega by mu g. You won't get that 4 though. Check it out again. So the friction, if omega is going that way, the friction will be acting backward in circular. You're getting it? The friction is opposite to the velocity and the velocity is tangential. This is how the friction will be. Right? So if you take this thin ring, at a distance x and thickness dx, the frictions are actually acting tangential like this. Observe one thing, all these frictions will form a couple. Basically, the net frictional force is 0. Getting it? So this body will not translate or something. Center mass will be at the center only. It will not move at all. So if you see here, net frictional force is 0. But torque is not 0. Getting it? Torque is not 0 because if you see, all of them got torque is in the same direction, anti-clockwise. In this case, clockwise. So how do we find that? First, let's find the mass of the ring. Mass of the ring will be total mass of the disk by pi r square. This is your sigma into area of the ring, which is 2 pi x dx. We have done this multiple times. Hope you remember this. The area of the disk will be circumference into that small thickness dx. Total mass by total area into dx. So this will give you 2m by r square into x dx. This is your mass of the ring. And the friction on the ring, now remember, this friction is the tangential force, okay? We are taking all the tangential forces. We are not literally adding it, we are just taking a tangential force. It will be mu into mass of the ring into g. Then the torque on the ring will be, now all these frictions are at a distance of x. That is the radius of the disk, which is x into friction on the ring, which will be mu into 2m by r square x dx g. So 2 mu mg by r square x square dx. So there, this is the torque on one ring. And you can clearly see here it is increasing with x, meaning the bigger the ring, the more the torque you have. That means the outermost rings will have more torque, right, compared to the inside rings. This is the torque on one ring. But remember, the disk is actually a combination of all these rings. So when you take the torque on the disk, it is a summation of torque all on the rings. Like I keep saying, the integration is actually easy. The headache is converting all this. It is simply an x square dx integration. 2mg by r square integral x square dx from 0 to r. And this would be 2mg r cubed by 3r. This is the total torque acting on the disk. Have a look at the steps. Any doubts on the calculation of torque? Clear with this? So once you got this, the torque on the disk must be I of the disk into alpha. So torque on the disk is 2 mu mgr by 3. And you remember the moment of inertia of a disk about the center? So that's what I'm saying. If you don't know your ICA values, you're gone. After doing this much, if you don't know your ICA values, mr square by 2. So we get alpha is equal to 4 mu g by 3r, which is constant. So if it is constant, I can use my standard kinematics equations. Omega final is equal to omega initial plus alpha t. Finally, it will come to rest. Omega initial is omega naught. Alpha will be 4 mu gr by 3r. Therefore, time will be 3r omega naught by 4 mu g. Check. So that becomes your circular kinematics. Please have a look at the steps. Yeah. Arya, where did you miss 4? Right, Utsa. Any doubts on this? All clear with this? Let's see one more. Shreyan, clear with this? Rishi? Pratyasha? Vedika? Sudiksha? Shauna? Great. Next one. Remember the disk, how we did this. You will see two more varieties of these questions, one in fluid mechanics and one again in electromagnetic induction. That's the 12th standard chapter though. This one is a good one. I think if you got this, you really understood a lot. So let's say I'll take a square plate. Here it is hinged. And here there is a string. In the second case, there are two strings. Third case, there are two springs. Square plate, mass M, side A, side L. Then what you did, you cut it here, and you cut one of the spring. Initially, system was at rest. These are strings. These are springs. Find A center of mass and alpha of the square plate just after cutting. Three different scenarios. Hinge, string, and a spring. First was easy. First one is kind of like a hinge thing, right? You know that. So how to do the hinge thing? I'll show you the first one. See, whenever you see a hinge, your life actually becomes kind of easy because the hinge is a fixed point. That's not going to move. So if you write the forces, we have Ny, Nx, and don't forget Mg will act on the center of mass. Perfect. There are only three forces. This thing will rotate with alpha. So your center of mass will be here. I'll not draw this shading thing. So this will go perpendicular to this, which is A center of mass. So if you find torque about the hinge, only mg is there. So you know how to do that. Extend the line, drop the perpendicular. This will be L by 2 is equal to mg L by 2. But do you guys know I about the hinge for a square plate? What is I about the hinge for a square plate? We did this. So if you have a square plate, you want moment of inertia about this hinge. This is your center of mass. We have to use parallaxes theorem. This will be ml square by 6. This distance will be L by root 2. So I about hinge will be I center of mass plus md square. If you do this, you will end up with ml square by 6 plus ml square by 2, 2 by 3 ml square. I hope you remember this. There, this was the problem here. 22C. Square plate, moment of inertia about the edge. This is what I was saying. If you don't know how to calculate moment of inertia, you're gone. Matlab, forget about even doing tough problems. Your basics only will be gone. This is where people find it difficult. If you think about this, this is exactly like cooking. You cut all your vegetables and keep them ready. As you have to cook, you just have to keep adding them. So if you don't know your moment of inertia in the exam, will you spend so much time deriving and thinking how to find I? You will slow down. You will not get time to do the tougher parts of the question. 2 by 3 ml square alpha is equal to mgl by 2. Therefore, alpha will be 3g by 4l. And a center of mass will be, that would be L by root 2 alpha. There you got it. Check your answers for the first one. 3g by 4 root 2 alpha. Right, Arya, the first one is right. Right, Ishman. Check karo ho gaya. See where it messed up. So that first one is actually easy one. What about the second one? What if there are two strings? Second one, I don't remember the answer there, but that looks wrong. ये थोड़ा ज्यादा आ गया ना तुझे 6g by 5. नहीं, that is alpha क्या?
Yes, sir.
How will the center mass go? Direction.
So the center of mass will move like downwards only
Okay.
initially.
ठीक है, चेक करते. टॉर्क किस पॉइंट पे लिया तूने?
Sir, I took torque and then I took pseudo force
नहीं नहीं,
again.
which point? Pseudo force भी लिया.
हाँ sir, about the string point.
You must have messed up right there. That would be a very bad point to take torque. Do you know the acceleration of this point?
Yes sir, I got it using relative motion.
नहीं, ठीक है, देखते हैं maybe. What is the catch with the B point, everyone? You cannot take torque about this point, huh? You know why? Do you really think after cutting the string, the square plate will just swing like this? The picture will become like this, everyone. This is how it will go, na? This string itself will start swinging, isn't it? This point A is not fixed. This point A itself will go in a circle. Are you getting it? You cannot take torque about point A. That is the main catch in the second part of the question. So how do you approach that? Take a minute, then I'll show you. B ka 6g by 5l, 3g by 5. That looks... Samyak got something else, Arya. You got double of him. Attention to him. I don't remember the answer. Dekhte, 2 minutes. Do the third one in the meantime. I don't remember the answer. How to do the second one? Try. Let's see. I don't remember the answer, but this is kind of like that problem, where you kept the rod on a smooth surface. Listen to this thing. What are the forces? Step one, remember again, I am not doing anything new other than the steps. Your tension, your mg. That's it. There are only two forces. Same story. Since horizontal forces are zero, center of mass cannot go left and right. A center of mass must be vertical. And this must be going with alpha. You can't take torque about this point since A is accelerating. So we get a no slipping condition here. Actually, we get a string constraint. So this point is going down with A center of mass. And this point is also going here with L by root 2 alpha. This angle is 45 degrees. Can this point have a vertical acceleration? Since the string is always tight, you cannot go up and down, isn't it? If you go up, string will become loose. If you come down, then the string will break. So acceleration of A along the string must be zero. That is your constraint. Because the string is not moving along the string, it cannot stretch. Must be zero. That will actually give you the third equation. String cannot stretch. So we get A center of mass is equal to L by root 2 alpha cos 45. Please check you got this equation. So A center of mass will be L alpha by 2. This is the relation between them. Next thing, force equation, mg minus T is equal to ma COM. Now, which point you will take torque? You can't take torque about A. You will take torque about center of mass because A is moving. If you take torque about center of mass, then will be tension T into L by T is equal to I center of mass alpha. For a square plate, I center of mass will be ml square by 6. That will give me ml alpha by 3. This is equation 3. Please check your equations. If you got the same equation, then we got the same answer. Force equation, torque equation, string constraint. Any doubts on the equations? There are three parts to the problem. The force equation, the torque equation, and the constraints or the no slipping condition. One of them will keep coming. And if you notice, this is the theme which is going on continuously. So then let's solve. mg minus T is ma COM. T is equal to ml alpha by 3. A is equal to L alpha by 2. What do you want to find? You want to find A and alpha. So take T, dump it here, take this thing, put it here. mg minus ml alpha by 3 is equal to ml alpha by 2. M goes off, then alpha will be 6g by 5l. Check. Right, Arya, I think you got the same thing. Then you'll get everything else. So be careful here. The system will actually move like this. Your point A itself is swinging. After some time, but the question is anyway just after cutting. Sure with the second one, everyone. What about the springs? Out of the three, springs are the easiest one actually. They look the scariest. The second is the toughest one. How to handle springs. Think for a minute. Let's see. Do you guys remember the difference between a string and a spring? In a string, the tension can change suddenly, whereas for a spring, it takes time. And this argument, right, we discussed in detail in laws of motion. And this was an important discussion. If you guys remember, just where is that? This one's tension in springs and strings. If you take a string there and if you put a block, tension will suddenly change. But if you take a block and put it, the spring doesn't care. Spring will say my initial elongation was X, so I will continue to exert the same force. And based on this, we did a lot of questions. Do you remember cutting off springs? So just after cutting, the tension in the spring still remains same. So same story here. So this guy was pulling with Kx and this guy was pulling with Kx. This is before cutting. And this was mg. So Kx must be mg by 2. So the spring doesn't care about anything else. It will exert the same force. So after cutting, the spring which you got, the tension became 0. But this spring will continue to exert the same force Kx, which is mg by 2. Your weight is mg by 2. And you can clearly see there are no horizontal forces, so center of mass has to go down. That's one important thing. If there are no forces in the horizontal direction, it will always go down. This is alpha. You can clearly see mg minus kx is equal to ma COM. A COM is equal to g by 2. Torque about center will be mg by 2 into L by 2 is equal to I center of mass alpha. Mg L by 4. I center of mass will be ml square by 6 alpha. Alpha will be 3g by 2 L. Check. So the main statement is that just after cutting, spring force doesn't change. Clear with this? Any doubts on this? Yeah, we can discuss after that class. Patience.
Sir, I have a doubt
Any,
in this question.
bolo na.
Sir, I kind of followed a different method here, but I don't know what went wrong there.
Tell na re.
Okay,
Sab
sir.
discussion के लिए बोलो ना.
Sir, in this question, the third part, what I did was I found a point along the mg to kx diagonal
Okay.
where both the torques are equal, and I assumed it to be on rest.
You're saying you'll take a point somewhere here?
Yeah, on that diagonal where both the torques of mg and kx are equal.
Okay.
And then I assume that point to be in rotational equilibrium, means that
But
is
what
the
is the
inertial
guarantee?
point.
What is the guarantee that point is always at rest?
So because the torques will act as a couple there.
But that point can have transition acceleration.
Maybe I messed up there.
तो pseudo force आएगा ना then. So what you're saying is fine. Torque तो निकाल दिया, but there's no guarantee it will be at rest ना. So you're assuming that point will never move. मतलब no matter what this does do, that point is always there. That doesn't work ना. Meaning about that point, the torque is always 0. That is not true. Maybe that is why it is not working. Clear with this? There, it's a good one. So again, I'm telling you, whatever we did today, please make sure to resolve them again. Take a rough paper, sit with them, try to solve the questions again. It won't take more than 20 minutes, right? That will actually help you to remember, it will help your subject. If you don't revise them, then there's no point if you're coming and watching it like a movie theater. Okay, with that, we'll wrap up for the day. So we'll catch up again on Tuesday. We'll continue from here. Next class, we will do even more problems. We'll do a little more variety on this. right? So there, I think we almost did 36 problems. So make sure to solve them again. And do remember there's a test online till tomorrow night. So make sure to give it. There'll be no extension this time. So any doubts, anything else, please stay back and ask, or else you're free to leave. I'll see you on Tuesday, same time. So take care.